In this video we are going to prove this. This is a very exclusive video because this proof is one of the proof that is very hard to find in the internet. So let me start. We are going to for the claim again, you need to know squeeze theorem because we are going to take use of it, and we are going to use limit laws. So you need to have covered those two, then you can understand how I do all of the stuff. So I'm going to need a circle, okay, a rectangle, triangle, something like this. So I'm not an artist, so this is how I came up with. We are going to take use of this figure here to derive most of our equation. Okay, so we are going to use nothing but what is on screen to solve everything. So first we're going to be interested in the area of the small triangle here. So again I need to tell you that the radius is equals to 1. So I have just one here, I have just one here. So to find an area of this triangle, I'll have to find the height. The height, because hypotenuse is 1, is going to be just adjacent sine. Yeah, it's going to be just sine. It's going to be just sine theta. That is going to be our height. So we can find the area of a small triangle with half base is, this is 1, base is 1, and height is sine theta. And then from this equation we can just say that this is going to equal to sine theta all over 2. I'm trying to keep everything minimal because the video seems to be long. So let's move our focus on the area of there is a piece of slice there. I hope you see it. This piece of slice, this triangle plus that sort of an arc there. So to find its area, we're going to use basic math. We know that the area of the whole circle have to be pi r squared, but we only want the small part, the theta part, only this piece of slice. So we just want parts of the theta all over. What is the theta of the revolution of the circle? It will have to be 2 pi. So from this we know that r is 1, so this doesn't change a thing. So this pi will cancel this pi, and this area is going to be theta all over 2. So let me just remove all this because we know that this area is going to be theta all over 2. And I'm also interested in another area. I'm interested in this area of a big triangle. I'm also interested in, I can find this, let me say I want to find this. I also already know the base. I need to find the this one. So let me just call this side K for explaining purpose. So we're just going to say tan theta will have to equal to the opposite, which is K all over the adjacent, making this is 1. So we now know the height is tan theta. So from this we know that the height is tan theta. So we're just going to again come back here. The area of a big triangle now, it's big like this. Area of a big triangle is equals to half base times height, and height is tan theta. And from this we can see that this simply says that tan divided by 2 tan theta divided by 2. Okay, we have obtained very useful results to use on our proof right now. So we notice that this area that is here, this area that I'm trying to draw, is the smallest area. What is it? This is the area I'm talking about. So sine, you know that sine theta all over 2 is smaller than the next one, the pizza slice, of which is theta over 2. And the pizza slice is also less than the big triangle, of which is tan theta all over 2. Because there are 2's all over, I can just, all these 2's, I can just cancel them. To continue with my problem, I will have something like this: theta all over 2 theta tan theta. Okay, so the 2's will disappear, right? But we can just also divide by sine, because remember, okay, I didn't tell you that for us to go to using first principle to solve this or to find this derivative, we need to have sine theta all over theta. We need to find the limit as theta approaches 0. So this is what we want. So we don't have what we want here. We're trying to make this thing contains this. So that's what I'm trying to do right now. So I can just divide by sine everything. And let me write 10 in a 10 as sine theta all over cos theta, and then multiply by 1 over sine theta that I'm doing all over. Okay, so the signs are not going to change here. Why they're not going to change? Because our problem, we are working at 0 up to 2 over pi over 2, which is the first quadrant. So sine is positive, so multiply by sine doesn't change a thing. We'll have sine over theta, and here we'll have 1, and here we'll have the sine will cancel that one, we'll have 1 over cos theta. So the next thing from here, remember what we wanted? We wanted this on the other side, so we need to flip the whole thing. So it's going to be sine theta all over theta, and if I flip, I'll have to change this to be cos, and this was looking the other way, to be look the other way. Okay, why I changed the sign here, or the direction of the inequalities? Because let me say I have 1 over 2 is greater than quarter. Quarter is like this, right? So if I can flip this thing upside down, I'll have 2, and this side I'll have 4. Obviously inequality will go the other way, so that's why I changed the inequality signs there. Okay, cos theta. So from here we can use the squeeze theorem, right? The squeeze theorem says that if I can find the limit of this and find the limit of this and find this limit the same, that will be the same limits for this one. I have another video on squeeze limit, using squeeze theorem to find the limits, so check that video out. Okay, so what can you do now? Let's find limits as theta approaches 0 of 1, of which is just going to be 1. Okay, that's good. And let's also find limits of cos theta as theta goes to 0. So as this goes to 0, there's supposed to be an equal sign. I can just plug 0 there, and if I plug 0, cos 0 will have to be 1 again. So because of this function are the same, we can conclude that the limit as sine theta over the limit of sine theta over theta as theta goes to 0 will have to be 1 again. So we have obtained the most powerful part of our proof. This is it. So what else we need to know before we go to the first principle? We also want to know that the limits as theta goes to 0 of cos theta minus 1. I think this is the last piece of the puzzle before we say we are almost done. So this will be just quite a long video, but that's not what I intended, but I'm trying to make this thing clear as possible. So we're just going to multiply by a conjugate here. I remember I have theta on the bottom. It's going to be cos theta plus 1 all over cos theta plus 1. And then from that, I can, on the top you see difference of 2 squares, and I think it's going to be cos squared minus 1. And if you notice this for metric identities, let me just write lim theta goes to 0. This is all equals to negative sine squared theta. So here I have negative sine squared theta all over here. I'll have theta cos theta plus 1. Let me just remove this, not part of my work. What else I need to see right now? Okay, I can also write this like limits as theta goes to 0 of negative sine all over theta. We have seen this before. Hope you can recognize this. And here we'll have sine theta. Remember I had sine squared there. Cos this was supposed to be bracket here. Cos theta plus 1. So from here we recognize this. It just says a negative 1 there, so it's going to change to negative 1. If I go back, what did we prove? We proved that is equals to 1, because of the other one here, which is the constant, it's going to be 1. So I'm just taking the limits now. So as theta goes to 0 here, and we know that sine 0 is 0, so this is going to be 0. Let me write it like this: 0 all over, I don't need to do this, but I'm doing it anyway. Cos 0 will have to be 1 again, plus 1, for it really doesn't matter because we just have 0 to change everything to 0. So we have proven something that is also important. Let me put it here. Limit as theta goes to 0 of cos theta minus 1 all over theta is equals to 0. So this is the second piece of the puzzle. Okay, with all this work done, we can now derive using the first principle. So we want to find the limit as h approaches 0 of sine x plus h sine h minus sine h all over h. This is the first principle, so I have nothing to explain here. So limit h approaches 0. Please bear with the video, make sure you finish this, because on the end I'm going to show you something very important and how you can just figure this thing out or remember it. So back on the video, we're going to use compound. We know this from your trigonometry. You can just say sine x cos h plus sine h cos x. We already had that one, minus sine x, that is all over h. So we are almost done. I'm very sorry for a long video. Okay, so now we are here. What I see, there is a common factor here and here. I can try to take it out, and if I do take it out, I'll just take out sine x. here all left with cos h, they're all left with minus 1, and here that will be just plus sine h cos theta. And let me just, because there's h is for everything that is in here, let me just divide it, not dividing as like in math, let me just separate it like that. Okay, so let me just take the limits from now, or do I need to? Okay, let me just do it like this. Okay, things that have that don't have h, they have nothing to do with their limits, so it is not their fight, it will just go out. For the sine x, it will just go out, and I'll take a limit here, and then we know this limit again. We can recognize this. We can recognize this first. One of the things that we proved, that we said it's equals to 0. Go back on the video if you've forgotten. This is what we're facing there. Come back here. So plus, we also know this. Let me go there. Again, limits as it goes to 0. As it goes to 0. We know here, let me check again, it was equals to 1, so we can just go back here, make this equals to 1. Yeah, and now we're saying again the limit of this one as h goes to 0. This thing doesn't have h, so it's have nothing to do. Oh, did I miss? Oh, there was a type error here. I just noticed it. I was like, where the theta is from? It's supposed to be x, yeah, because I got this from here. Yeah, so there is x here. So as h goes to 0, this is not changing because it has x. So I've skipped many steps here because I assume that you now can work with your limits, limit laws. So this is going to come back as cos theta. I'm saying theta again, okay, x. I should have used theta anyway. Okay, now we know this will go to 0, and then our answer is going to be cos. I'm saying theta again, x. So we're saying that to find the gradient of the sine graph, you'll have to use cos. The part that I promised you, the bonus part, let me just work on it now, because I promised you to not leave the video. If you came to this far with the video, congratulations. You're about to learn something new again. So let's look at the sine graph. I think it should be like this. I should have used a different color. This is the sine graph. So we know that the gradient here is positive, and here the 0. And here the gradient is negative. Here it is 0. And here it will be positive. So it has some stationary points just here and here. Okay, so we need a function that can cater this. The only thing that we need to say again, I'm working with sine. Sine graph is periodic, so it goes on and on, like just like a wave. So its derivative should be periodic again. So we're looking at sine, tan, obviously not looking to other functions. So let's just narrow our looking, that we're just looking for these trig functions of which they are also periodic. So we're looking for a function that goes positive and then goes to 0 and become negative and negative. If I can just show you the answer, this function goes positive and goes to 0 and goes negative, and here it goes to 0, and here did I miss something? Oh yes, I missed something. I did miss something, so I made a mistake, I think. So let me just work it like this. This function here should be on this quadrant, This function here should, all this part should be in the lower quadrant, and this function could be on this. And if you notice, what we're trying to, or what we're landing on, is a function that is, it should be on this quadrant. We say, I tried to change the column. Okay, so we're saying it should be here, and this here should be 0, and then we're saying here it should be on the negative quadrant like this, and here it becomes 0, and here it should be like this. So we recognize this function exactly. This function is our fortunately it is a cosine function. So that was very interesting. So if you find the video informative, please don't forget to subscribe, share with your classmates, also comment. Thank you.